Next up on our agenda, our last presentation of the day, bringing it home. We have Dr. Alexandra Holloway, Freddie Wang, Mark Mimoni, and Neil Abkur of NASA JPL presenting These Wheels Are Made for Arcing, 2 new mobility commands to reduce wheel wear. All yours.
Thank you, Brandon. So excited to be back. Thanks for having us. Hang on just a sec. Let me get my notes up. Okay. All right. Hi, everyone. My name is Alexandra Holloway. I am the lead for flight software for Mars Science Laboratory at JPL. And today I'm delighted to introduce These Wheels Are Made for Arcing, 2 new mobility commands to reduce wheel wear. And I hope you guys all have the song playing in your head now. It's my contribution to this session. Joining me are Neil Abkur, Mark Mimoni, Freddie Wang, who are going to be telling you about the story of the new ARC commands. So next slide, let me tell you about the agenda. So first, Mark is going to tell you, he's going to lay the foundation with the MSL mobility and wheel wear background. How do we move the rover? How the rover moves itself. Then Neil will talk about implementation, the math behind the 2 new commands, and how they were built into the flight software. Then Freddie will talk about verification and validation and how we tested the 2 new commands. And with that, over to Mark.
Okay. Can you hear me? Yeah, okay. So thanks for joining us. So I'm going to talk about some background on how Curiosity moves, and so to give you some context for the changes that we're making with this flight software change. So next slide, please. So Curiosity is a 3rd generation 6-wheel Mars rover with a rocker bogie suspension. It follows in the footsteps of the other pictured rovers here, the Sojourner rover and the sister rovers Spirit and Opportunity. Curiosity has been driving on Mars for nearly 10 years. We landed in August 2012. We're still going, and it's likely to continue to operate for many more years. But as you can see in the pictures on the bottom there, an unexpected amount of wheel degradation was first noticed after 490 Martian solar days, or sols. That's about 1.5 years. And that discovery has led to several mitigation strategies. So it was an unexpected problem. In the short term, what we did was we limited our drives to be less than 20 meters every day. And for every step along the way, we had a human looking at the terrain to see if it would be safe or not. The next step was a medium-term update, which was the science team noticing that they could characterize the kind of terrain that was most problematic and actually identify it from orbit. So they gave us new strategic routes to follow over the long term, years, not just days. And those changes to our drive path really helped a lot. They helped mitigate the damage, slow down the rate of degradation. And then in the long term, we had a strategy for making software changes to improve the performance of the system to further mitigate any damage from the terrain. And one of those updates was done several years ago. It's called Terrain Adaptive Wheel Speed Control. And it allowed the rover to, in real time, at 8 hertz, update the speed of each wheel as it was climbing over different rocks. And that helped reduce the forces on the wheels. But today we're going to talk about 2 new flight software commands that we plan to add this year or shortly thereafter that will help take us into the 2nd decade of Mars operations. Next slide, please. So this is a diagram showing you some of the basic mobility commands that we have. And you can see the icon is for Spirit and Opportunity. So this architecture goes way back. It's the same kind of strategy we've been using since Spirit and Opportunity on Curiosity and even into Perseverance. So there are 2 main types here. We have basic mobility commands and autonomous mobility commands. Basic commands are very simple. You can command an arc, which is forward motion with a fixed curvature in the wheels, And so if you want to drive straight ahead, just steer the wheels straight ahead with some motion. But if you want to curve, if you want to turn, then you build so that they're pointed at a central turning point off to one side. And that can get you a heading change as well as forward or backward motion. So we have arc turns and we have relative turns where you can ask the rover to turn, say, 30 degrees to the right, 30 degrees to the left. We can also command relative to a fixed heading. We can say we want to turn so that we're facing 90 degrees, facing due east. And so these are some of the basic commands here. Now, arc commands are interesting in that they're commanded what's called an open loop fashion. It means that the motion of the wheels is predetermined in advance, and the motion just stops whenever the wheels have turned enough to reach the expected rotation amount. So you basically pre-compute, if we were on flat ground, how many wheel rotations would it take to go 1 meter? You command the motors to move that much and you stop. So it's not actually sensing anything. It's not sensing its distance, it's not sensing its heading, or it's not acting on any sensed heading. So that's an open loop command. In contrast, turning is a closed loop command. We have an inertial measurement unit on board that detects the heading change that's actually occurred using gyro integration. And so when you command a turn in place, you're pretty confident that when you stop, you're actually facing your commanded heading, whereas with an arc, you don't really know that. And then finally, we have autonomous navigation. And with autonomous navigation, we have, it's one basic command that has a lot of options, but basically you say, not that you want to turn a certain amount or drive a certain distance. You say, I want to go to this location, this XY location. And that's relative to some fixed site frame in the nearby terrain. And the rover will get it there. And the way that it goes depends on what other modes you have enabled. You could tell it to drive itself autonomously, avoiding any geometric hazards in the way. You could tell it to drive with the visual odometry, so it's measuring its motion as it goes and compensating for any slip as it goes. Or you could tell it to just go in the blind and just sort of take the fastest route there. And what it'll do then is at every step, it'll just pick the arc that gets it closest to the goal. So autonomous navigation gives you current information, but it doesn't really support fine positioning. We generally use autonomous navigation to get in the vicinity of a goal, but not really right on a goal. So next slide, please. So this basic framework has certain implications for wheel wear. The basic mobility arcs don't adapt well to unexpected changes, but the autonomous go-to can't do fine position. So in order to reach goals, we have to sort of blur the lines between them. And on the MER mission, we added, late in the game, like a few releases into the flight software, we added the new Arc Until command. This was sort of a combination of the two. It's an Arc command, so it's open loop. It doesn't really know where it is. But we gave it a little bit extra smarts. We said, once you get to a point where you're at a goal location, or you're beyond the line, tangent to the rover, hitting the goal, then you want to stop. So it's a way of saying, let's arc until we get to the goal, but not beyond. So that was a helpful addition because it lets you, use some sense data, use some knowledge to not go any further than we want. And having added this, we actually made this the standard pattern for driving every leg of commanded motion on the rovers. We would generally command a go-to to get in the vicinity of a goal, a turn to point at the goal, and then arc untils to reach the goal. So that way we don't have to rely on any autonomy to get us there, which might get confused or have sort of weird oscillating behavior if you don't exactly reach the goal point. This was a way to follow a pattern to get us to the goal using a turn and an arc until. Next slide. So that's been very helpful, but that arc until only lets the rover adjust the drive distance, not its delta heading. And the problem is that a turn in place has more use of the wheels. We have to steer the wheels in at like about 45 degrees. All the corner wheels steer in and then have to steer back. there's extra motion required to do the turning. And so to avoid that, we thought that it would be helpful to add these new commands for Curiosity. We actually considered commands like this on MER, but we thought it wasn't needed. Well, the reason we need it on MSL now is that the wheel wear considerations have forced us to do this. So let's go to the next slide. So as I was saying, the current precision approach to a point requires this turn in place with a lot of steering. If we could instead let the rover pick its own heading, pick its own arc curvature to get it to the goal, that could reduce the steering quite a bit. Instead of going 90 degrees back and forth, you would just have to turn a tiny bit to get to the right orientation to get to the goal. So in order to accommodate that and improve the long-term potential use of the wheels, as the mission enters its second decade, we're adding two new commands. The Arc2 command is going to calculate its delta heading, calculate its curvature, to put it at the goal without going beyond a certain path length. And the Arc-Until command, Arc-Until2 command, is going to drive along a certain arc, but it's going to stop once the rover enters a waydisc or other criteria of Arc-Until, like if you don't want it to go past the goal. Arc2 is going to calculate the heading. Arc-Until2 will stop once it's gotten to that point. So next slide, please. So this is going to be helpful for future mission planning because we can basically consider replacing the turn to and Arc-Until that we've been using up till now, which has all that extra steering, with Arc-Until2 and Arc2, because the Arc2 will minimize the steering change needed to reach a goal, and the Arc-Until2 gives us high precision in pointing at a goal. It'll drive along the commanded arc only until it's actually pointed at the goal. So these two are going to give us the same functionality of reaching the desired goal point with less steering in order to help with wheel wear. This is a new update that we expect to be deployed ideally this year, but the actual deployment date isn't set yet. So we'll have to wait and see, but we're looking forward to getting these new commands on board. And now here's Neil to tell you about how the commands are actually implemented.
Hello, can you hear me?
Yep.
Okay, great. Okay, so we're going to talk about the underlying math behind these two commands. So first is Arc2. So instead, so we want to get to the nav goal that's to the right and in front of the rover. We want to be pointing at it. So instead of turning in place, gathering all that wheel wear while we're steering, instead we're going to do an arc of a certain length that will have a change in heading that will point the rover at the nav goal. We don't know a priori what that change in heading is until we are at a certain place and we know where on board the rover knows where it is in relation. So the inputs to this are the goal and the distance that we'd like the arc to be, and the output is a certain arc with a certain distance and change in heading. Next slide, please. So we can do some trig based on the final position of the rover. So the final we can figure out as a function of both the arc equation, which is using the radius of the arc and also the change in heading. And then we can compare that to the concept of the waydisc. So there's a waydisc around the goal of the rover. We don't want to go all the way to a goal, like say it's a rock we want to sample. We don't want to approach close to a certain distance to that goal. So we know we have two constraints on the location. We can solve what that final position is. We can take the two equations at the top, set them equal to each other, solve for d, our distance, and that's a function of change in heading. Got two equations that just have the change in heading as an unknown. and we can find the change in heading as that final value 2 times a tan 2 of, and it comes out very simple, just the goal in y and the goal in x plus the waydisc distance. Plug that back into the equation for D, and you get your solution. And that's assuming that the rover meets the waydisc. So if you then look at that final position and it isn't meeting the waydisc, you know that that final, you're not driving far enough to meet the waydisc, and it's a slightly different problem. Next slide, please. So if you're not meeting the waydisc, effectively, you're reaching a waydisc with a distance where W is unknown. So you can solve for the change in heading. It's the change in heading is equal to the arc tangent of these two quantities, which are in and of themselves the equation of the change in heading. So we don't have a closed form solution for this equation. Any enterprising trigonometry fans who want to talk to me and offer me a solution, I'm all ears in the Slack. But so what we're doing currently is we do a simple bisection search. So we've got the delta heading is equal to this function of change in heading. We subtract one side from the other, and we wait until this equation changes signs. And we do this so we loop over potential values of change in heading. We find a good, relatively small interval, then use bisection search to narrow it down further. So next is the arc until 2. So with arc until 2, there's a certain arc that we want to do. We know the change in heading that we want to do. We know the distance that we want to do. But there's 3 potential ending criteria that we want to consider. We want to stop if the rover is pointing at the goal at any point in that arc. Can you go back, please? Thanks. We want to stop if the rover ever touches or enters the waydisc. And finally, we want to stop if the rover ever gets to the closest point along the arc to the goal. We never want to travel farther away from the goal. Next slide. So the first criteria is that we want to stop when we're pointing at the goal, and this ends up being fairly similar to the last equation, and at least what it looks like, but where we know the curvature of the arc, it's not unknown. So we can use the tangent, and we can use the linear combination of sinusoids to find a closed form solution. We get that we get a couple interesting properties from the solution. So we get a plus minus, and that relates how there's 2 solutions for pointing the front of the rover at the goal and pointing the back of the rover at the goal. We see that there's an arc cosine, and if the input to the arc cosine is a magnitude greater than 1, arc cosine doesn't have a solution. And that corresponds to cases where the goal is within the arc that the rover is tracing. And so there's no, and you can keep looping and looping and looping, and it'll never point at the goal. So there's no solution in that case, and we'll never meet this end condition. So we can ignore it. We also get that plus 2 pi n at the end, and that shows that if you're looping around and around and around, you'll hit the equation again and again. So we have to look at different values of n and find the smallest amount of traversal that gets us pointed to the goal. Next. Next, we're concerned about the rover meeting the waydisc, and it ends up being a linear combination of sinusoids again. For similar reasons, some arcs may never enter the waydisc. They may the waydisc may be totally inside or totally outside the arc that the rover's tracing. And if it is touching, if it does enter the waydisc, as it's traversing an arc, and theoretically it could be going in circles again and again, it'll enter the waydisc and leave the waydisc again and again. And then the final end condition. Next slide, please. We're concerned about the closest approach to the goal. So we take the equation between the center of the arc and the goal position, and we trace that line, and we find the intersection between the arc and the line traced between the goal and the center of the arc. And that's relatively simple, but a familiar 2 by n shows up again. So we take all these 3 end conditions, we find the smallest fractions of the desired arc that an ending condition applies to. So say we get, 0.1 arc violates this end condition, 0.2 of the arc violates this condition. We find the smallest one, and then we determine the fraction of the arc that is valid to continue. And so from these 2 equations, we get arcs back that are valid arcs that will get us so that we are pointed at the goal or meet one of these end conditions that gets us close to the goal and gets an arc, so it is moving at the goal and is applying all the desirable behavior that Mark mentioned earlier. And next slide, that brings us to the end of my contribution. Ready?
Hello, can you hear me?
I can hear you.
Cool. Okay. All right. I will talk about our V&V strategy. So the test cases that we developed for V&V exercise the nominal functions of the new commands, as well as the off-nominal usage. We want to show that the commands work as intended, but also use them in ways that are not intended to show that they're robust. Our V&V flow starts with our simulations, and then we run for record in the real world. The simulations I used during the procedure development to help understand the behavior of the commands better, and also to baseline our expected outcomes. The run for record happens on our vehicle system testbed. That's our VSTB for short. It's the functionally identical twin of Curiosity on Mars, and testing these commands on the VSTB gives higher confidence for usage in flight. The selected test conditions are the test conditions are from arbitrary and infinite passive positions. We can pick whatever we want, but the methodology that we chose to go with is based on earlier mission testing of existing mobility commands. So we simplify everything into 8 basic directions and one close to or at the rover origin, and we express these in generic Cartesian coordinates, +x, +y, and so on. And then the actual goal conditions will depend on the specific test case. Now, next slide, please. So here are 2 examples. The first one shows Arc2 pointing the front at +x and +y. This is an example of a nominal use of the command. And the second example on the bottom shows Arc2 pointing the rear at +x and +y. No idea why we would use this second case in flight, but doing so, again, we show that the commands are robust to all of the inputs that we can possibly give it. Next slide. So there were a couple factors impacting the development of V&V. First was the location of our testbed. For a long time, it was in a tiny sandbox. So the goal coordinates were chosen to minimize motion so that we can stay within it. And the procedure has test cases that could not be done in the sandbox because we knew at some point we would move out of it, but we didn't know when. And those are and conflicting needs for the VSTB caused test delays. So the schedule was very fluid and we had to adapt our procedure to accommodate that. The other big factor was understanding the command behavior. My initial understanding of the commands was mostly right, but wrong in a lot of ways because the way the shorthand descriptions were didn't fully describe the edge cases. So there were a lot of small nuances that had to be picked up in developing the procedure, running simulations, correcting our expected outcomes. And yeah, we hope to be testing this soon.
All right, I think it's my turn again. So in conclusion, 10 years into its 2-year mission, we're still updating flight software. We're looking for new ways that we can do things, new capabilities that we can fold into the flight software, including driving things. And I invite you guys all to come see the talk about MSL's new flight software tomorrow. Shameless plug, it's mine. Tomorrow afternoon, it's the last talk of the session, and we'll be talking more about the kinds of things that we're folding into the flight software. So commands that were considered too complex for earlier missions became useful to help mitigate this unexpected wheel wear that we were seeing. So we had to come up with different ways of driving or or different commands that would help us drive in a more safe way for the wheels. And just so you guys know, the slides keep auto going forward because there's an auto advance thing in the slides that I didn't take out. Slide operator, you're doing awesome at going back every time it goes forward. Thank you so much. These new mobility commands, the Mob Arc 2 and Mob Arc Go 2, are going to be incorporated into drive planning as a new way to reach waypoint goals while minimizing steering. And we expect to deploy this in this year with the R13 software release of MSL flight software, hopefully. And with that, thanks everybody for coming. Thanks to my co-presenters and the entire team who made this presentation happen.
All right, thank you so much. We do have some time for a few questions. Two questions actually that are a little bit related. First question from Leonidas. What's the required precision of the trigonometric computations needed? Do you use floating point calculations or fixed point? And how many bits?
Yeah, I can talk to that. So we use floating point, not fixed point. It doesn't need to be super precise. The amount of, any given arc that's actually done on the surface of Mars will be subject to all sorts of minor disturbances. A wheel goes over a rock that the other ones don't go over, and so that one will go slower, and you'll get, disturbances in the actual final position and pose of the rover. And that's part of why we want these commands, so that we can do arcs toward the end of our AutoNav procedures that are readjusting to look at the goal, because we don't have that level of precision. We can't predict the future when we're driving with that level of precision.
Okay, and a related question from Amelie. Arctangent being computationally expensive, have you thought of coarse approximations for some of this math?
Yeah, so short answer, it's fine. Long answer is that the arctangent isn't something that is like going on and on over again. It's not going over multiple cycles. It's not being done at a high rate as the rover is moving. It is, we have a sequence, and it's in that sequence there's a command that is arc2 to achieve this mission, and it's one command that happens once during a sequence, and that sequence results in one to a couple arctan computations. So this is not something that's in a high rate loop. It does not need to be efficient. That's not a good place. Trying to make it more efficient is not a good use of resources.
Okay. Give a few more seconds for any other questions to come in. All right. Thank you all so much for your time and contributions this afternoon. All right.
Thank you.
Thank you all. All right. That's the end of our agenda for day 3 of the Flight Software Workshop. We'll see you all right back here at 11 a.m. Eastern Time tomorrow for the 4th and final day. See you all then. Thank you very much.